Yes, yes, friend. Now, the heading here is a video expression for centripetal acceleration. I told you in the last video, that when a body moves on circular path with constant speed, then direction keep on changing, and due to that change in direction, there is acceleration in the motion which act towards center along radius and is called centripetal acceleration. Here in this figure 1, this is figure 2. A body is moving on circular path with constant speed v. Its velocity are v1 and v2 at time t1 and t2 at point A and B. Body goes from A to B time interval t2 minus t1. At point A, velocity v1 and linear velocity along tangent. This is the direction of velocity v1. This is velocity v2 here. And v2. Now, acceleration, as you know, it change in velocity per time. In figure 2, this is v2 minus v1. This is one method, and this will represent v2 minus v1. So you can see 2r is towards center. Whatsoever be the position here or here, but acceleration change in velocity will be towards center along radius, and that is why I told you that this acceleration in case of uniform circular motion, which is called centripetal acceleration along radius towards center, it has been proved here, sir. So let in figure, you can write here, let in figure, a body moves on circular path of radius r with constant speed v. Let its velocities at point A and B are v1 and v2. The body goes from A to B in time interval t2 minus t1. Body moving on circular path with constant speed v. Velocities are different v1, v2 because of change of direction. Magnitude is same. Modulus v1 equal to modulus v2 equal to modulus v. So to find the change in velocity in figure 2, vector tq equal to v1 and q PR equal to V2, and hence vector QR equal to V2 minus V1, and modulus this equal to, I take here delta V. So delta V is the change in velocity per unit time. Okay? Now, if delta theta is small, then you know delta theta equal to tan delta theta equal to here delta V upon V. You can say modulus V1 is equal to delta V upon V. Actually, I told you that when theta is very small, tan theta equal to theta, sin theta equal to theta, and then theta equal to arc upon radius. Concept is there. So delta theta is equal to delta V upon V. Now dividing by delta t on both sides. Delta t means t2 minus t1. Dividing this equation by delta t, we get delta theta upon delta t equal to 1 upon v into delta v upon delta t. But here direction will be changing towards center every time the body comes from here to here. So we take instantaneous value, putting limit delta t tending to 0 on both sides. On both sides, we get limit delta t tending to 0, delta theta upon delta t is equal to limit delta t tending to 0, 1 upon v delta v upon delta t. And you know, when we replace limit, we write this expression as d theta upon dt. D theta upon dt is equal to 1 upon v into dv over dt. Now, just I told you d theta upon dt. What is this? D theta upon dt. But d theta upon dt is equal to omega, angular velocity. And dv over dt is equal to acceleration, A, acceleration of motion. So we can write here omega equal to A upon V. What is V? Linear velocity, magnitude of linear velocity, or A equal to V into omega. This is one relation. A here represent magnitude of centripetal acceleration. A here represent magnitude of centripetal acceleration. V represent the magnitude of linear velocity. Omega magnitude of angular velocity. But you know omega equal to V by R. But we know omega equal to V by R. So A equal to V square by R, or A equal to R omega square. Using this relation here, we can get the relation. A equal to V square by R. Here A is the instantaneous value of acceleration, magnitude of instantaneous acceleration. So direction of acceleration towards center. In vector form, how we can write it? Vector A to the right towards center minus omega into vector R. Omega square into R, sorry. Omega square into vector R. Vector R has direction. Listen me carefully again, I am drawing the diagram. P point is there, position vector taken along this x-axis positive. Happy? This is vector R. Acceleration inward. So I have put minus sign here. And this centripetal acceleration is also called as radial acceleration. So we can write it AR equal to R into omega square. This thing. AR. In place of centripetal acceleration, people call it as radial acceleration. Why? Because it acts towards center along radius. Direction towards center is clear from the diagram. In diagram v2 minus v1, that is qr vector towards center. So direction of acceleration towards center q, because direction of acceleration is the direction of change in velocity. And there v2 minus v1 in figure 2 has direction towards center. Now, think the case if body moves with variable speed. If on circular path, body moves with variable velocity, speed, I should say, then at every instant, along with radial acceleration, there will be linear acceleration, which will be along tangent, and hence is called tangential acceleration. Acceleration. This is important to understand. So, if velocity is varying, then AT and AR will be at right angle. If at an instant AT is the tangential acceleration, AR is the radial. If AT and AR are the tangential and radial acceleration respectively, then resultant acceleration A is equal to under root AR square plus, because you know when two vectors are at right angle, then the resultant will be under root R1 square plus R2 square. Direction of this acceleration, direction of A will be tan theta is equal to AT upon AR. Listen me here. Here the circular path. Now this is AR here this way. This is AT here this way. So resultant AT plus AR added like this. So this is at theta. So it is AR upon, मैंने उल्टा लिख दिया ना, AR upon AT. ऐसे जोड़ सकते हैं, yes, हाँ, ऐसे कर सकते हैं, yes. It is AR, this is AT, हाँ, this is correct. AT upon AR, making it theta with like this, and it will be like this. So direction of acceleration in circular motion is along radius towards center only when velocity keep changing without change direction, but magnitude remains same. when body moves on circular path, or you can say when there is uniform circular motion, only then acceleration will have direction towards center along radius. But if speed is variable, then along with radial there will be tangential acceleration, and direction will depend on the direction. If velocity decreasing, at will be in the direction of magnitude of speed increasing. But if magnitude of speed decreases, then at will be downward, because direction of acceleration is change of velocity, and then AR is this. So resultant will be like this. So direction of acceleration depend in change in velocity. In case uniform circular motion, there is only centripetal acceleration, which acts towards center along radius. But if it is variable speed, then at every instant, centripetal acceleration always there. AR equal to B square by R or R omega square. But along this AR, there will be AT at every time, whose direction will be changing. But in case of uniform circular motion, there will be centripetal acceleration, and value of centripetal acceleration average over a cycle. Here AR this, here AR this, and so average acceleration over complete cycle will be 0 in case of uniform circular motion. So this is the concept of centripetal acceleration. Why the direction towards center? Because direction of acceleration is along the direction of change in velocity. I told you very earlier the direction of acceleration not necessarily always along velocity or opposite to velocity. It may be at any angle also here. And in case of uniformly circular motion, acceleration is at right angle to velocity. Please note it. In case of uniform circular motion, direction of acceleration at every point of the motion. If the velocity here, this, if it is here, it is this. So acceleration always at right angle to velocity when the motion is uniform circular motion. We will be meeting in next video with numericals. Thank you.